Okay, so we've also studied turbulent laminar bands in other geometries. Poiseuille flow. So here's a simulation of turbulent laminar. I'm not going to spend as much time. Obviously, it's the same kind of thing. Here is the same kind of diagram as in the as before, where this is the z direction, which is the direction perpendicular to the bands, and you see we're lowering the Reynolds number. You see very different Reynolds numbers here. But that doesn't mean anything. That's something that has to do with the convention for Reynolds number, which we will discuss very shortly. And here we see a wavelength of 20 half gaps rather than 40. And again, we'll discuss that in just a moment. It will turn out to be somewhat significant. And now we have something new. They're not going up straight like that. They're moving. Well, remember, Poiseuille flow is different from Couette flow. And I take this opportunity to talk about symmetry. I was talking about Couette flow as being it's centrosymmetric, meaning you do simultaneous reflection in x and y. So this goes to that. Simultaneous reflection in x and y is the same as rotation by pi. And forget about z for the second. Whereas Poiseuille flow does not have that symmetry. It has a different symmetry, which is reflection in y, and there's definitely a sense of motion, the motion in which you're pushing it. You might think the same of Couette flow if you just moved one of them, but recall I said we could go into a frame without it would be completely equivalent, where the average velocity was 0. But even if we go into a frame where the average velocity of Poiseuille flow is 0, which we can by having plates that move backwards while we blow, we can have the average velocity be 0, at least numerically. That still doesn't change the fact that there is no symmetry between downstream and upstream. In Couette, there is, because the top is going upstream and the bottom is going downstream, or the other way around. Okay, so that really changes everything in a way that it didn't mention in the symmetry class, but I would have liked to. That is to say, there's a difference between left and right. This does not have reflection symmetry. And you see that the fact that I remember when I said, and what does that mean that we have traveling waves? And that person in the back, who maybe is here now to receive this compliment, said, what this means is that you can have traveling waves the other way. And I said, oh, this is someone who understands the class. You remember that? A few days ago. Okay, so you might say, I say they're going this way, and the answer is not, oh, they could go the other way. No, they have a way they want to go. The Poiseuille flow is being blown. It has a direction. The fact that you have things going this way does not mean you have things going this way. This way is with the flow, and this way is against the flow. A situation without reflection symmetry. Still, as you see, here sometimes they're going to the left and sometimes they're going to the right. That is to say, I have done these simulations in a frame in which the average velocity is 0. Otherwise, they would always be going with the flow because, well, you're blowing it away. So it can, it's not strange for it to then start going against the flow. Remember, the mean flow is 0 here. Even though the mean flow is 0, but there's still a difference between right and left. Okay? Anyway, so an additional measurement that's possible in Poiseuille flow is the speed with respect to the mean, which changes sign. It's quite small, as you see, if you divide by the Poiseuille velocity scale here. Okay, but it does have a change in sign.
But
and
you don't know the mean until you've done the simulation.
It's the this is something I always get confused about. You're talking about.
You can still do the simulation.
Yeah.
And then figure out what the mean was later.
Isn't it the mean of the? You can impose the mean being 0 all the time during the simulation, right? And I think that's what I do. Green's functions. Okay, so now let me talk about something which is. May seem like a technical detail, but I like it. As we said, the wavelength was 20 and half gaps, whereas in Couette flow it was 40 and half gaps. And we said the Reynolds number is different, and that is because this is the typical convention in Poiseuille and Couette flow. As we said, the half gap, this is 1, and in Poiseuille flow this is also 1, and then this maximum velocity is 1 here compared to 0 here, and here it's 1 and minus 1. So you can see, actually, that the conventions, although they look kind of similar, they're really quite different. This is really a shear layer with one sine where you have a delta U of 1 and a delta Y of 1 here. And so if you base your Reynolds number on that shear layer here, that's quite different from basing it here on the difference delta U over 2 and the difference delta Y over 2. You get a factor of 4 difference. So a Reynolds number of 300 in Couette flow is approximately like a Reynolds number of 1200 in Poiseuille flow. Hence the difference. In addition, the velocity scales are different. As we say, if this is really the shear layer in plain Poiseuille flow, one of these, and yet you're calling this one, and you're calling this thing here one, while this is half the shear layer, and this is the whole shear layer, you can see there's a factor of 2 difference, as is written here, a 2 difference in this, in the height of the shear layer. Hence, when you say 20 half gaps, where really a half gap is a whole shear layer, whereas here it's half the shear layer. So when we say 20 half gaps for Poiseuille, we're saying 20 shear layers. I think that's right. A half gap is a shear layer, 20 shear layers. And here we're saying, when we say 40 half gaps, we're saying 20 shear layers, because the shear layer is of height 2. Right, so they're really the same size. And this, it's not, I should say, this helps you understand that that's the case, that that's what Poiseuille really is. It's 2 superposed shear layers. And people, I'm not sure that is appreciated sufficiently. Here's another thing that shows that. Those pictures that we saw of Couette flow, we saw pictures like this of Couette flow. This was, recall, the mean flow for a laminar turbulent banded pattern. Yes, we saw a red and a blue. This is, you see, it looks different because the aspect ratio has been stretched so as to make it easier to see. So this is Couette flow. And if you reflect it like that, you see that that looks a lot like the pattern that you get in Poiseuille flow for a laminar turbulent banded pattern. So you see, again, evidence that Poiseuille equals 2 Couettes. And here's another piece of evidence, is that force balance. We saw this already. This was the place where this was the laminar part where we had no turbulent force, excuse me, is this what I want? I don't know, let me not do this. We don't have time. But there's, everything points to the idea that Poiseuille is 2 Couettes. Okay, now we're going to introduce another flow, which we've been calling Walef flow. Other people can call it Kolmogorov flow. It's a flow in which you recall how when we did convection in the 2nd class, you remember we put on free slip boundary conditions. And why did we do that? We did that because we liked to use trigonometric functions in Y. We thought that was simpler. Not just we thought, it is simpler. It allowed us to do the whole calculation analytically. Now this will not allow us to do the whole calculation analytically, but it will still simplify things. So we put on free slip boundary conditions, top and bottom. You recall that, of course, always makes problems. After all, in the lab, you really do have your, I don't know how you do Walef flow in the lab, but even forgetting about the lab, your question would be here, what made Couette flow happen? It happened because we were pushing this plate this way, and we were pushing this plate that way. If we impose free slip boundary conditions, how are we imposing the shear? Well, the answer is we put it in with a bulk force like this. We put a bulk force in the equations, a sinusoidal bulk force. And that creates a flow that looks like this. Okay, that's the laminar flow in Walef flow. It's sinusoidal. Okay? And I say sometimes called Kolmogorov. And okay, we were in convection, why we studied the free slip case, because it gave the same qualitative behavior. It really gave us the explanation for convection, a lot of the properties. And so this is Walef who introduced this flow. And let's show some of the advantages. The plane, we already said it's sinusoidal functions, but let's look more specifically. The laminar flow, of course, is a straight line, which is awfully simple for plane Couette flow, and it's sinusoidal for Walef flow, which seems a little less simple. But if we look at the mean flow, if we average in time at a turbulent profile, a turbulent flow, we average in time, those of you who study turbulence know already that plane Couette flow, it has these boundary layers. It's kind of constant in the bulk, and another boundary layer here. right? You know that you have to go from right to left. Here you're going from right to left linearly, gradually from one to the other like that. And here you go mostly, you go to 0 here, you go to 0 here, and here you hang out at 0. Everybody agree with that? Everybody who's studied, you're familiar with this S. How many people here do something? I was told that many of you did boundary layers or turbulent flows or something like that. No, but so this S-shaped profile maybe looks familiar. That's the mean flow for plain co-ed flow when you're fully turbulent. So this is not so great. It's kind of complicated. This one was a nice line, but this one was a S-shaped curve. Whereas if you do simulations of well left flow, 'cause that's the only way you get the turbulent mean, you do simulations of well left flow, it goes fully turbulent. We'll show that in just a moment. But its turbulent profile, it doesn't have to do something at the boundary because it doesn't need to go to 0. It doesn't have a boundary layer. It's like this. So this one gets to be a nice straight line, the well left flow. And so it turns out that well left flow basically captures what we want to study is, we don't like the boundary layers. The boundary layers, you need a lot of resolution for the boundary layers, and you have to think about the boundary layers versus the bulk, and that. We don't like the boundary layers, or maybe we don't like the boundary layers. Maybe we'll find that nothing works without the boundary layers. But let us try getting rid of the boundary layers, and we can do that by taking our well left flow to be a model of the inside of plane coherent. We're going to say, is well left flow like getting rid of the boundary layers? And of course the answer is yes, it is. So we're considering a well left flow that's this big, and we're asking, is that just like cutting this out? And it turns out it is, and we can show that in many ways. Sorry, here is a turbulent laminar band in plane co-ed flow. Okay, and this picture now you've seen many times. And this is turbulent laminar band in well F flow. And it looks just like this, except as if you'd taken scissors in this black place. It's as if you'd really there's a boundary layer here because you have to go to 0 at the end. You can't have some velocity here. You've got to be green. Green is 0. And you've got to be green over here, so you have this rapid change. But for well F flow, it has no such problem. We can just cut, and really it looks just the same. It's as if we cut out the boundary layers. And here's where we're doing it. We cut it out. It's not exactly the same, but it's very similar. We've just cut out the plane co-ed flow boundary layers. And we're saying that well F flow is like that. Okay, I just mentioned this just in passing, but indeed, here are the turbulent bands of plane co-ed flow that you've seen many times. Well F flow also makes turbulent laminar bands. Here's a picture from full simulations of well F flow. It makes them, and it makes them at the same Reynolds number if you correct for the size, saying that you're only considering the interior and this and that. So really, it really is a lot like plane co-ed flow. And this tells you something very important. First of all, it's numerically important. You don't need the extra points you would normally need at a boundary layer. But also theoretically important. It means you don't need the wall. There's this whole thing called the law of the wall in turbulence. And the wall is considered really important, but you don't need the wall. Turns out you only need the shear. The only thing that's important is you have a gradient in velocity, not that you have boundary layers. Straight, that's the way it turns out. Okay, so I said all this. Okay, we can then, since well F flow is so smooth and simple, remember in Lorentz, for the Lorentz model, we did a truncated model. We had we didn't have many functions, and we saw how far we could go with it. Here we're going to do the same thing because it's so nice and smooth in Y, because it has no boundary. Y remembers the cross-channel direction, and now we've cut out the boundary layers. We're going to try modeling with just a couple of functions in Y. Normally you need something like, you do a proper simulation, you need 33 grid points, 33 Fourier modes between them. You have those boundary layers, you worry about it. Here we're only going to do 4. We're not going to pretend it's that accurate. It's going to be a model the same way Lorentz model is a model. Well, hopefully better than that. But anyway, we're going to just go with it. We're going to have this, just a few functions here. And it turns out that with less resolution in Y, with bigger spacing in Y, effectively, you actually don't need as much resolution in X and Z. That size restriction gets propagated out, and you only so you really have an enormous economy. You have about a factor of 50 economy in resolution by using this well F flow. This model well F flow, rather. Okay, here since everybody likes movies, here are the movies of bands being formed in regular plane co-ed flow, in well F flow, And then in model Wallet flow is where you have only a few basis functions in Y. And you'll see they all form bands. The model Wallet flow now has a different Reynolds number, as you can see. Okay, so here it is, forming bands. So you see it's a, let's see, go faster. What makes it go faster? Is it L that makes it go faster? Let's make it go fast. There it is. Right, so you agree it's forming bands. Okay, so we think, okay, it's okay to, oh, I didn't mean to do that. It's okay to study model Wallet flow. It's going to give us, help us to study. Now we return to our question before. We had the question of characterizing the lower bound of existence of those turbulent laminar bands, remember, or turbulence in general. Okay, we had the upper bound, which we decided was 430 by that maximum of the probability. We want to characterize the lower bound. And this is I'm going to introduce a bunch of hard physics, but since I don't know much about it, I hope I will present it in a way that anybody can understand it. So this is our question. What is this lower bound? Okay, what's the lower bound in numbers, but also what does it mean? How do you define it? So we use here ideas introduced by Pommeau in 1986. Here is something. Here's a simulation of something. And you see that you have these little black regions. That's supposed to be kind of turbulence. And you see it kind of looks like bands a little bit. They're shorter. Okay. And the question is, are they going to all go away? Is there a minimum amount you need to maintain it? That is to say, is the transition continuous or not? If you need a minimum amount of turbulence, or you get no turbulence at all, then it's discontinuous. Supposing you can't be turbulent with less than 20% turbulence. Okay, that's the question we want to ask. That's the big question. And okay, so here we saw this. Yes. Okay, so this is the question: is it continuous or discontinuous? Let's see. I guess I'll get back to this. A discontinuous one would look like the one on the left. A continuous one would look like the one on the right. This thing about the universal exponent, let's get back to it later, maybe. Okay, here's a minimal flow unit. You saw it before, Gibson 2x4x6 approximately. Let us show, okay, here's a band unit. This is now not a tilted band unit, but this is the minimum rectangular unit you'd need to observe the bands. And you see everything's kind of done to scale. This would be, recall that this is about a roll pair. So this is about the gap, and that's about this. Right, so this is to scale. So what you'd need to observe the turbulent laminar bands properly without using one of those skinny domains that we used would be a domain about this size, which is really correct in ratio to one of these minimal flow units. Okay, so that's big, right? We got around that, we didn't do it. But that domain is very small compared to the domains that we actually simulate. We simulate domains like this, in which that minimal flow unit is like a pinprick, you couldn't even see it. And here are the domains that people have used before to study this question, compared with ours. You see the different dates. The experiments, Prigent and Dochot, remember they discovered the bands, and this is about the size of their domains. And Kirsten Avila did experimental study of a domain about this big. Lemoult et al. Did tilted domains like ours that were about this size, and you see our system is huge. Okay, and why do we need such a huge domain? This is what the system looks like when turbulence is, it's not so regular, but it's kind of well established. The bands haven't decided to make themselves into a structure, but you sort of see the remnant of the bands. But when you're very near critical Reynolds number, this is what it looks like. And you can see that if your domain is too small, you're not going to, here, you could easily think that there's no turbulence at all. You're not going to get the right statistics at all. In fact, for no finite domain can you get the right answer. You always have to, if you're in a finite domain, you always have to have a minimum of 1 pixel or 1 grid point. right? So, you know, there's you can't go to an arbitrarily small, for any size domain, you can't go to a point, you have to have at least, I mean, even if there were no physical rules, you'd have to have it at one grid point, which would be 1/1,000,000th, right? You couldn't go below 1/1,000,000th if you had 1,000,000 grid points, right? But more than that, you need more than that, because you can't just have turbulence at one point and nobody near you. You definitely see that given that you're trying to study things that look like this, it depends a lot with the sizes, that you can easily be wrong and think that you have nothing or the wrong percentage if your domain is small. And these people thought they had very big domains. Look, these are turbulent laminar bands. You remember how big they are compared to the streaks. You can see them as, you know, you barely see them. I don't think you even see them at all there. That whatever little horizontal stripes you see, that's the width. So the domain is huge. You see that our current domain for simulations is 2,500 by 2,500 in terms of the half gap. So really, really, really big. And how are large domains possible? Well, we already answered that question just before. We're doing Walef flow, which captures, we claim, the interior of plane correct flow effectively. We have evidence for that. Walef flow has been studied by these people. It produces bands. All this we already saw. And now we're going to answer the question of whether it's continuous or discontinuous. Obviously, if I'm here telling you, you know, based on what I told you and the smallness and the bigness of the domain, our answer is it's continuous. This is what we find. Okay? Now, we get back to this exponent that we talked about, this 0.58. What is this 0.58 thing? Well, this has to do, okay, and you see that we've gone to a lot of trouble to show that this is a, this here is the turbulent fraction as a function of Reynolds number. And remember that the Reynolds number for this model Walef flow is not the same as Walef flow. Those go down. And when we do a log-log scale, in order to detect a power law, from bifurcation theory in dynamical systems, I'm very used to an exponent of 0.5. Everything goes like square root of. You remember how many times we wrote x equals plus or minus square root of mu? How many times did we write that? A zillion times already in the last guy. Okay, but here I'm writing 0.58, and that's not an inexactitude in 0.5. That's not a mistake. That 0.58 is a true theoretical result that is based on the theory of directed percolation, which I barely know, and hence I will tell you just a tiny bit about it. Here it is. Here's directed percolation. Its theories put up by the big physicists, people like, I guess, like Goldenfeld, but Rossberger, the big names and people from, it's not so old. It's from the 1990s. It's a certain model. And the idea is it's a class of transition person by liquid percolating through granular media, and it's purported to be universal in the same way that everything I've been telling you about dynamical systems is universal. The difference being that I understand the universality of dynamical systems and I do not understand this, but I take their word for it. Lots of important statistical physicists have calculated those kinds of exponents. What it's supposed to describe is the competition between two states, one excited and one non-excited, and that you remember from the excitable media part. If you are not excited, you're never, and you have no neighbors that are excited, you're always going to remain. And the same thing with laminar. If you're laminar and you're sitting here and no turbulence comes by, you're just going to stay laminar. You're just there. You need something to excite you, and that is usually your neighbors. So you can maintain a certain amount of turbulence. It's not that you remain turbulent, but it's like a disease, not like a disease, like an epidemic. If you have an epidemic, you're passing the disease to your neighbors. It's not that the same people are sick. It's that you need a certain amount of sickness to pass around to the neighbors, and that will maintain a certain level of the disease. But you don't get sick if there's nobody around you who's sick. If you're sick, you might recover. But if you're well and if everybody around you is well, you're never going to get sick. Right? And it's the same thing here. This is the idea here, that you have turbulence that can infect the laminar part. And if you have enough turbulence going around, then although the turbulence tends to die, it is meanwhile infecting the other ones, which then infect the other ones, as we saw with the excitable media. So there's a lot of theorists have studied this. They've done lots of theory and numerical simulations, and they have all these exponents down to 3 digits or more. You can look it up in Wikipedia, but it has almost never been observed in experiment. They really, really believe in it, but it has been observed once in experiment. And now, possibly we can consider that this is twice. It depends whether you consider this to be I mean, this is more like an experiment than what the statistical physicists were looking at, but it's not really a real physical experiment. But we have observed all these characteristics. So what do they, the people in directed percolation, what do they predict? They predict the dependence of the turbulent fraction. That's what we were looking at before. We were looking how much of it, what percentage is turbulent. This is supposed to be time. In this case, this is 1D. Ours is 2D. This is 1D in space. So what fraction is turbulent? And how does that vary as you change the control parameter? It's going to go to 0, yes, but with what law?
And just, so their original model